So chemical reactions can be exothermic. They can release energy, heat into the surroundings, or they can be endothermic, where they are absorbing energy from the surroundings. There's a quantity called enthalpy, which is just kind of hard to get your mind around. Enthalpy is the quantity of thermal energy emitted or absorbed by a reaction. So enthalpy isn't something that you can measure directly, but you can measure the difference in the enthalpy. So what we call the enthalpy of reaction, or delta H reaction. And you might wonder, why is enthalpy abbreviated with an H instead of an E? Well, we've got so many things we use letters for that E was taken. Enthalpy, it's okay to think of it as heat, and so the H might make more sense that way. So it's the amount of thermal energy or heat that flows when a reaction occurs at constant pressure. The at constant pressure part is sort of the small print. In Chem 1A, we go deeper into what exactly that means, but for now, we're just going to leave it here. So the sign of that heat of reaction depends on the direction. So energy coming in, energy going out. It's a little bit like transactions on your checking account. You use your debit card, and some of those transactions are positive and some are negative, right? Some is money coming into your account, some is money leaving your account. The sign is the same here. When money leaves your account, it shows up as a negative, right? Because it goes away. When energy leaves a reaction, that's a negative delta H. When the reaction absorbs energy from the surroundings, that's like money coming into your account, you got paid and you make a deposit, it's a positive transaction, right? So positive delta H means that energy is coming into the system. So here we have, we often draw little energy diagrams like this where we represent energy being higher towards the top of the page. In an exothermic reaction, the reactants have more energy to start out with than the products do. As the reaction occurs, the chemicals lose energy, and that energy goes out into the surroundings. And so that's an exothermic reaction. Endothermic reactions start with low energy in the reactants. The chemicals are absorbing energy from the surroundings, and so the products end up with more energy than what was started. Any questions? So for an exothermic reaction where energy is leaving, delta H is negative. So if we look at the combustion of methane, methane is the main component in natural gas. So if you have a gas stove at home, this is the chemical reaction that's occurring when you light the stove. So methane reacts with oxygen. Combustion reaction forms carbon dioxide and water as the products. The heat of reaction for this is negative 802.3 kilojoules. Remember, kilojoule is a unit of energy. So what this is telling us, the negative sign tells us it's an exothermic reaction. The energy is going out into the surroundings. And this quantity is the amount of energy that happens when 1 mole of methane burns. If you burn a little bit of methane or a lot of methane, you're going to get a different amount of energy released, right? You think about like a Bic lighter. It's not methane, but same idea. You're just burning a little bit. There's a little bit of heat. You fire up one of those turkey fryer burners, you know, that are just ginormous, right? We got 2 of them. They give off a lot of heat. They're burning the same thing. Why do they give off more heat? Because they're burning more gas, right? So the amount of energy released depends on how much stuff is being reacted. So just as convention, just how we do it, when we write a chemical reaction like this with the heat of reaction here, this quantity refers to, or this is the amount of energy released when this reaction occurs, and we're interpreting this as moles. So 1 mole of methane, 2 moles of oxygen. When that combusts, 802.3 kilojoules of energy are released. If you burn 2 moles of methane, you'll get twice as much energy. Okay? Endothermic reaction, energy is going into the system, so it's positive. Here's an example of an endothermic reaction. Nitrogen and oxygen reacting to form one of my favorite chemicals. No! Because all caps means yelling, right? So this is no nitrogen monoxide. You guys have to wake up. You're supposed to laugh at that? Okay, positive 182. So this absorbs 182.6 kilojoules when 1 mole of nitrogen and 1 mole of oxygen react. If you reacted half a mole of each, it would absorb half as much energy. So this kind of summarizes what I've already said. The magnitude of that heat of reaction is for the stoichiometric amounts as written. So you may see it written different ways, and then the delta H would change, and it's for the molar amounts in that balanced chemical equation. So here is the chemical reaction for the combustion of LP gas, liquefied petroleum. It's mostly propane. So propane burns with oxygen, forms carbon dioxide and water, and for every mole of propane, it releases 2,044 kilojoules of energy. So we can make conversion factors. Oh yay, more dimensional analysis here. We can make conversion factors from the relationships in this equation. We learned earlier in this chapter that you can make a conversion factor for 1 mole of this for every 5 moles of oxygen. But now we can also use this 2,044 kilojoules per 3 moles of CO2. So we could say there's, 2,044 kilojoules per 5 moles of oxygen. Or we could say we're going to produce, forgot the unit. We're going to produce 4 moles of water for every 2,044 kilojoules of energy that are lost. So you can take the delta H and relate it to any one of the terms in the chemical equation. Would it be a negative? Let's see, do I talk about that? Okay, since you mentioned it, often in the homework, the absolute value of heat is requested because words are used to convey the sign. So it's a little bit, again, like money. If I said, I paid you $5 for, I don't know, something. I paid you $5. Would I say I paid you negative $5? No, because paid tells us which direction the money's going. The money's leaving me and going to you. And that's the same for the chemical reactions. Here, 4 moles of water for 2,044 kilojoules. We're going to see the direction of energy transfer most likely in the words used in the question. So let's do an example. I get lost sometimes. So ammonia reacts with oxygen according to this equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of ammonia. Now this is saying associated. Does that indicate a direction? No, it doesn't specify a direction. So then we're going to have to clearly specify in our answer, either by using positive and negative signs or by using words, what direction the energy is going. So we're going to approach these problems are stoichiometry problems. And I'm going to approach them the same way I do any stoichiometry problem. You read through the whole question first, and then go through the question and look for any numbers that are given. Those are typically important. So 155 grams of ammonia. I'm going to use the balanced chemical equation to help me organize the information. So under ammonia, I'm going to write 155 grams. And then I'm going to look for what are they asking me to find. They want heat in kilojoules. Well, this is the term that specifies amount of heat. So I'm going to put a question mark over here. Question mark, and they're asking particularly for kilojoules. So we can approach this as dimensional analysis. We need to find out what we're starting with and where we're trying to go, and then we can figure out how to get there. Well, this is the question mark. This is where I'm trying to go, and this is the only other information I have, so that's where I'm starting. I know some of you have this down pat, but a lot of you are still struggling with this. If you're still having trouble with stuff like this, you really, really do need to write the path. Because once you get the path written out, it'll fall into place. So this is where I'm starting, and I'm going to end up with kilojoules of energy. And then I have to figure out, how do I get from one to the other? Well, the equation here is saying that when 4 moles of ammonia react, this much energy is released. So I have a relationship between moles of ammonia and kilojoules of energy. So if I had moles of ammonia, I could get to kilojoules of energy. Every arrow represents a relationship that you know or can find out. Can I get from grams of ammonia to moles of ammonia? Sure, I just need the molar mass and I can calculate that. So that's my path then. Any questions? Once we have the path, we can write the equation. So 155 grams of ammonia. Each arrow represents a conversion factor. There's 2 arrows, so there's 2 conversion factors. Grams of ammonia to moles of ammonia to kilojoules. So those are the units that go in the numerator. Grams of ammonia to moles of ammonia to kilojoules. I'm copying the path down in the numerator. I take this unit and put it in the denominator, grams of ammonia, so those cancel. And I'm going to put moles of ammonia down here, so those cancel. Now I need numbers. This last term, kilojoules of energy and moles of ammonia, that comes from this balanced chemical equation with the delta H here. This is telling me that 906 kilojoules are released when 4 moles of ammonia react. So we can put a negative in here. Negative 906 kilojoules for every 4 moles of ammonia. This grams to moles, well, that's the molar mass of ammonia. We should be able to calculate that. And so then we get out our calculators. 155 divided by 17.034 times negative 906 divided by 4. And my calculator is showing me a whole bunch of numbers. I don't want to write them all down. So I'm going to do sig figs here. So 3 sig figs, 5, 3, and this is exact. So my answer should have 3 significant figures. So I'm going to write down 3 significant figures and then 2 extras just to be safe. Did anybody else get that number? Did I do my math right? Okay. When I'm rounding this number, I need to be careful. 2061 is not the same as 206, right? So I'm rounding to the nearest tens place. I can say, well, this is negative 2060 kilojoules. That's okay. Better is negative 2.06 times 10 to the third kilojoules. That's the best answer. Here it's asking for the heat associated. So I can give this as a negative number, which tells the reader this much energy was released. Or I can write a sentence and say the reaction released 2.06 times 10 to the third kilojoules of energy. That's like looking at your bank account and it says -5, or saying, I paid you $5. Sometimes words replace the negative sign. Any questions? Let's do another one. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? And what mass of CO2 is produced? So here we have another balanced chemical equation. What is strange about this balanced chemical equation? It's got a fraction in it. That's not how we normally do it. But it is balanced, and it does still work. So this amount of heat is for the molar amounts listed here. If you want to clear the fraction, then you also have to manipulate this. I would recommend just leaving it alone. Okay, so I read the question. I'm going to take that number and write it down. We're given an amount of energy. So I'm going to write that over here under the energy term, 1.5 times 10 to the third kilojoules is produced, right? So if it's produced, is that positive or negative? Well, producing something sounds like a positive thing, right? But you have to put yourself in place of the reaction. So I am the reaction. I produce energy. That means the energy leaves me, so it's negative. And then they're asking what mass of butane. And you might think, well, we didn't learn butane. How am I supposed to know? Well, we learned how to name this one and this one and this one. So maybe the other one is the butane. I wouldn't do that to you on an exam. So we're trying to figure out how many grams of that guy. So here we've got a number over here, and we've got a question mark here. We're starting with kilojoules, and we're going to grams of butane. So we're starting with negative 1.5 times 10 to the third kilojoules, and I'm trying to get to grams of butane, C4H10. What's the unit that comes in the middle? Moles. You remember the TV show Malcolm in the Middle? Okay, so I think of this as moles in the middle. When we're dealing with chemical reactions, there's usually moles in the middle. So if you're not sure how to get there, try going to moles. So if I knew moles of butane, I could get to grams because I can use the molar mass of butane. So moles of C4H10. And this term, minus 2658 kilojoules, that is for 4 moles of butane. So I can go from kilojoules to moles of butane using that one. When we did mass-to-mass stoichiometry, you had 2 mole terms in the middle. With energy, there's only going to be the one. It's a little bit shorter. Okay, I better start a little higher because I have another problem to do. Minus 1.5 times 10 to the third kilojoules times and a line times and a line. So I've got moles of C4H10 there and grams of C4H10. The previous unit becomes the denominator. Forgot what I was writing. So that these units are going to cancel out. Once I get all the units in place, I go find numbers. So I like to start with the easiest one. This one seems easiest to me because it's directly from the equation, no calculating involved. 4 moles of the butane and minus 2658 kilojoules. Grams to moles, that's going to be a molar mass. So that's 4 times 12.01 plus 10 times 1.008, 58.12. And I put my numbers in, negative 1.5 times 10 to the third times 4 divided by negative 2658 times 58.12. How many significant figures is my answer going to have? 2, because this starting number had 2. So as I write this answer down, I'm going to make sure I include 2 sig figs and 2 extras, at least 2 extras. And the unit is grams of butane. Here I'm rounding in the tens place. I need to be careful. 131 is not the same as 13. So I could call this 130, or better, 1.3 times 10 to the 2 grams of butane. Any questions? Yeah.
Since the kilojoules are negative, is the fraction under it always going to be negative?
Pardon me?
Since the kilojoules are negative, is the fraction under it always going to be negative too?
That's an excellent question. What's disturbing to me and to many students about these problems is that the negative signs are kind of, I don't know, wishy-washy. The way I wrote this problem, I put the negative sign on the amount of heat, and then I also used the negative sign listed over here. And so my negative signs canceled out, and I ended up with a positive mass. Sometimes you just start with this amount of heat, and then you stick this in with a negative, and you end up with negative mass, and then your brain should say, hey, wait a minute, I can't have negative mass. What happened there? Oh, I was just, a little loose with my negative signs. So what's best is either completely ignore the negative signs and think about it at the end, or embrace them and make sure that you write them everywhere that they need to be. Are we done with this problem? No, we're not. There's another question. What mass of CO2 is produced? So we could do this 2 different ways. We know the mass of butane that was used. We could go from grams of butane to grams of CO2, but that's going to involve 3 conversion factors. Or we can just start again with the quantity of heat and go to mass of CO2. So that's what I'm going to do. This time, as illustration, I'm going to leave all the negative signs out and think about them at the end. Because remember, the negative signs here just reflect the direction of energy moving. So 1.5 times 10 to the third kilojoules of energy is involved. Now, instead of going to moles of butane, I want to go to moles of what? CO2. And from moles of CO2, I'm going to go to grams of CO2. It's the same process, I'm just interested in a different chemical this time. So moles of CO2 down here, and kilojoules down there. All Always check that your units are canceling out. So this moles of CO2 in kilojoules. Here in the red, I'm ignoring the negative signs until the end. So for every 4 moles of CO2, there's an energy change of 2658. So 4 moles and 2658. And then here I need the molar mass of CO2. So 1.5 EE3 times 4 divided by 2658 times 44.01. Again, I'm going to have 2 sig figs. So 99.34 grams of CO2. 99 grams of CO2. Now, what will often happen to students is they see this positive number, they see that negative number, and so you put the negative in here, and then you end up with a negative mass, and you're like, oh, wait a minute, what happened? Well, if you think about it, producing, that means energy's leaving. So that's actually negative. So the mass is always going to end up being positive. Any questions? There we go.